Welcome everyone. Today we are diving deep into the backbone of process safety, the IEC 61511 Functional Safety Lifecycle. Whether you are working in oil and gas, chemicals, or power generation, managing safety instrumented systems, or SIS, is not just about installing a device. It is about a comprehensive management strategy. In this presentation, we will explore the comprehensive guide to managing these systems to ensure safety integrity is maintained effectively. We will be walking through the standard that defines how we prevent hazardous events and mitigate their consequences in the process industry. By the end of this video, you will understand the critical phases required to manage an SIS from its initial concept all the way to its decommissioning. So, what exactly is IEC 61511? It is the global standard dedicated specifically to the process industry sector. It acts as the implementation standard for the parent document, IEC 61508, but is tailored for the specific needs of industries like chemical, pharmaceutical, and oil and gas. The primary goal here is straightforward but vital: to prevent hazardous events and, should they occur, mitigate their consequences to acceptable levels. The standard introduces a cradle-to-grave concept. This means we aren't just looking at the engineering phase, we are managing the safety integrity of the SIS from the very moment we design it, through decades of operation, right until the day we turn it off and decommission it. It ensures safety is not a one-time check, but a continuous life cycle. On screen, we see the safety lifecycle model broken down into its 6 core phases. This linear progression ensures that safety is managed systematically from start to finish. It begins with analysis. This is where we perform the hazard and risk assessment, or HARA, to identify potential hazards and determine exactly how much risk reduction is required. We then move to realization. This phase covers the design, engineering, and verification of the safety instrumented system SIS to ensure it effectively meets those safety requirements. Next is installation and commissioning. Here, the system enters the physical world. We perform rigorous testing and validation to confirm the installed system functions exactly as intended. Once the system is live, we enter the operation and maintenance phase. This involves ongoing proof testing and managing any changes to maintain functional safety throughout the system's life. If upgrades are needed, we trigger the modification phase. This is a formal process that ensures changes are safe, often looping us back to the analysis phase. Finally, we reach decommissioning, ensuring the safe and controlled removal of the SIS from service at the end of its life. On screen is the IEC 61511 Safety Lifecycle. This diagram represents the cradle-to-grave management of a safety instrumented system, or SIS. To understand how this works, we must first look at the activities that frame the entire lifecycle. On the far left, we have management of functional safety and lifecycle planning. These are not single steps, they are continuous requirements. They ensure that throughout the entire life of the plant, we have competent personnel, clear roles, and defined responsibilities governing every action we take. On the far right, running parallel to everything, is verification. This represents the constant validation of our work, checking that the output of every single phase matches the requirements of the previous one, ensuring no errors are carried forward. The core technical work begins at the top with the hazard and risk assessment. Here, we identify the potential dangers in our process and determine the necessary risk reduction. This leads directly into the allocation of safety functions, where we decide which layers of protection, such as the basic process control system or the SES, will handle those risks. Once the risks are allocated, we enter the critical planning stage, the Safety Requirements Specification, or SRS. This document defines the precise logic, trip points, and integrity levels the system must achieve. This marks a crucial gate, Functional Safety Assessment Stage 1. We must verify the specs are correct before moving forward. Next is the design and engineering phase, where the hardware is selected and the application software is developed. After the design is assessed in Stage 2, the system is built, leading to installation, commissioning, and validation. This culminates in the site acceptance test to prove the system works in the real world. Before the plant can start up, we conduct the Stage 3 pre-startup safety review. This gives us the green light to enter the operation and maintenance phase. This is the longest part of the life cycle, where we perform periodic proof tests to ensure the system doesn't fail silently over time. Finally, the standard accounts for change. The modification phase dictates that any changes to the system must be strictly managed and authorized. Eventually, when the system reaches the end of its life, we follow the decommissioning procedures to safely remove it, ensuring no residual hazards are left behind. Let's start with Phase 1, the Hazard and Risk Assessment, or H&RA. This is the crucial first step of the life cycle. Our objective here is to systematically identify potential hazards within our process and strictly evaluate their severity and likelihood. You are likely familiar with the common methods we use here, such as the HAZOP, Hazard and Operability Study, or LOPA, Layer of Protection Analysis. We are essentially asking, what can go wrong and how bad will it be? The output of this phase is vital, a comprehensive list of hazardous scenarios that require specific risk reduction measures. Without a solid H&RA, you are designing a safety system based on guesswork rather than data. Once we know the risks, we have to allocate safety functions to different layers of protection. We start with the BPCS, or Basic Process Control System, which is responsible for maintaining normal plant operation. If that fails, we rely on alarms and operator intervention, alerting operators to abnormal conditions so they can take manual action. If the pressure continues to rise, we might rely on relief devices like PSVs to prevent catastrophic failure. Finally, when other layers are insufficient, we allocate functions to the SIS, or Safety Instrumented System. The SIS is our automated shutdown system, designed to act when all else fail. This brings us to the Safety Requirements Specification, or SRS. If you take one thing away from this video, know that this is the most critical document in the entire functional safety lifecycle. The SRS defines the precise functional and integrity requirements the SIS must meet to mitigate hazards. If the SRS is wrong, your entire design and implementation will be flawed, no matter how expensive your hardware is. It must define the safe state, does the valve open or close, the response time allowed, the specific trip points, the SIL target, and the process safety time. It is the blueprint for safety. Before we start buying hardware, we hit our first major stop, FSA Stage 1. This timing is critical. It happens right after the H&RA and SRS are complete. The goal is to confirm that our analysis is complete and that the SRS is clear and achievable. Why do we stop here? Because of the cost of errors. Solving a specification error at this paper stage might cost you $1. If you let that error slip through and have to fix it during operation, it could cost $10,000. This is a critical decision point where we must stop and assess before moving into the expensive design phase. Now we enter Phase 2, Design and Engineering. This is where we begin selecting technology, choosing the appropriate sensors, logic solvers, and final control elements. A major part of this is architecture selection. We have to determine if we need 1 out of 1, 1 out of 2, or 2 out of 3 voting to achieve the required SIL target. We are also designing for hardware fault tolerance, ensuring the system has enough redundancy and diagnostics to handle failures. Crucially, we must ensure the separation of SIS from BPCS. There must be complete independence between the control system and the safety system to maintain the integrity of the safety function. Design isn't just about drawing wires, it's about math. SIL verification is the process of mathematically proving that our design meets the SIL target. We calculate metrics like PFD average, probability of failure on demand, to ensure we meet architectural constraints. Then we address the software. Believe it or not, software is often the biggest source of systematic error. To combat this, we use limited programming languages like ladder logic or function block diagram to reduce complexity. We must avoid complex code and, crucially, use simulation to test the logic offline before it ever touches the live plant. This validation is key to catching errors early. With the design complete, we reach FSA Stage 2, the Design Assessment. This assessment takes place after detailed design, but before the equipment leaves the factory. Our objective is to verify that the design actually meets the requirements we wrote down in the SRS back in Phase 1. We aren't just trusting the vendors, we are reviewing the Factory Acceptance Test, FAT plans, and checking the SIL verification reports. This is our final paper check, to ensure the system theoretically works and meets safety standards before we physically build and install it on site. Next, we move to the physical world with installation and commissioning. This is critical because we must ensure the as-built system matches the as-designed system. This phase culminates in validation, often called the Site Acceptance Test, SAT. Think of this as the final exam for the SIS before startup. We perform end-to-end testing, verifying the complete chain from the sensor input through the logic solver to the final valve movement. We don't just simulate via software. We inject real process signals, like actual pressure or temperature, and we time the valve closure to ensure it meets the strict response time requirements. We are almost ready to run, but not before the most critical assessment in the lifecycle, FSA Stage 3, often part of the pre-startup safety review. This happens after installation, but before we introduce any hazards into the process. We run through a strict checklist. Is the H&RA complete? Is the SRS met? Are the operators trained? Are maintenance procedures ready? Only when all criteria are met do we give the go decision. This gives the plant the green light for startup, confident that the safety system is fully functional and ready to protect the facility. Now we enter the longest phase, operation and maintenance. This covers the 20-plus year lifespan of the system. The key activity here is proof testing. The concept is simple. If a safety valve sits open for years, you don't know if it will close when needed until you test it. We conduct these tests to find hidden failures and restore the probability of failure on demand, PFD, to good as new. This creates the famous sawtooth curve. We also need to consider test coverage. A partial stroke test might only find 70% of failures, whereas a full stroke test can find up to 99%. However, there is always a percentage of undetected failures we must manage. During operation, we face a silent killer, unmanaged change. Statistics show that 40% of accidents happen during changes. This is why management of change is crucial. The rules are strict. There can be no changes to set points, logic, or hardware without authorization and a full impact analysis. We must ask, does this change invalidate our SIL calculation? If we make a change, we must update the documentation, like the SRS and P&IDs, immediately. Uncontrolled changes undermine the safety integrity we worked so hard to design, leading to unintended and potentially disastrous consequences. Even if operations seem smooth, we cannot get complacent. This is why we have FSA Stage 4, a periodic assessment that occurs roughly every 3 to 5 years during operation. The goal is to review our actual performance against our design assumptions. We review actual failure rates of our equipment and compare them to the assumed rates used in our original SIL calculations. We also verify that proof tests are being performed on the correct schedule. We look at demand rates, checking if the safety system is tripping more often than we expected. This feedback loop ensures our safety calculations remain valid over time. Eventually, every system reaches the end of its life. Decommissioning is the final phase. This ensures the safe removal and disposal of the system. It is not as simple as just cutting wires. We must analyze the impact on any remaining active units to ensure we don't accidentally trip a live neighbor unit. We physically remove SIS components to prevent accidental use in the future. This phase also involves a FSA Stage 5 review to ensure the decommissioning process itself is managed properly and that no hazards are left behind. Safety integrity must be maintained right until the very last component is removed. Underpinning all these technical phases is the management of functional safety. IEC 61511 explicitly requires that competent people perform these tasks. Competency isn't assumed, it must be assessed and documented. Organizations must clearly define roles and responsibilities. We need a competent functional safety team in place, representing process, instrumentation, and electrical disciplines. Furthermore, training and awareness are non-negotiable. All personnel involved in the life cycle must receive appropriate training to understand their impact on the system. Ultimately, the standard provides the framework, but it is the people who provide the safety. To wrap up, let's look at where things commonly go wrong so we can avoid them. Studies show that 25% of compliance failures are caused by a vague SRS, simply not being specific enough about what the system needs to do. Another 20% come from copy-pasting SIL calculations, using generic data instead of specific application data. Leaving bypasses active too long accounts for 15% of failures, leaving the plant unprotected. And 12% come from treating validation as just commissioning, skipping the rigorous safety tests. Recognizing these pitfalls is the first step toward preventing them. In conclusion, IEC 61511 provides the necessary framework, but safety is ultimately a mindset, not just a checklist. It requires a strong culture of competence, vigilance, and continuous improvement. By understanding the full safety lifecycle, from the initial hazard analysis to the final decommissioning, and by actively avoiding the common pitfalls we discussed, organizations can build resilient safety systems. Our ultimate goal is not just compliance with a standard, it is the relentless pursuit of a safer, more sustainable future for the process industry, protecting both our people and the environment. Thank you for watching another video with us. If you found this video helpful, please like, share, and subscribe for more content on instrumentation and control engineering. If you have any questions, please leave them in the comments section below, and we'll do our best to answer them. Thanks again for watching.